These are probability note 6, independent events. Today we're going to focus on independent events and mutually exclusive events. Independent events meet the criteria. The probability of A, the symbol means and, B, equals the probability of A times the probability of B. In real life, this means the result of event A does not affect the result of event B. That's what makes them independent. Mutually exclusive events meet the criteria. The probability of A and B equals 0. And in real life, this means that event A and B cannot both occur at the same time. It also tells us that events can be independent, events can be mutually exclusive, events can be neither of the two if they don't meet either of these formulas. However, events cannot be both independent and mutually exclusive. We're going to look at 3 examples where you're going to be asked if events are independent, mutually exclusive, or neither, involving a dice roll and a spinner spin. For event A, we're going to look at a spinner spinning a show of 3, and for event B, the sum of the die in the spinner being 5. And what we'll look at is what you get inside here, which would be the sums of these different spins and dice rolls. Let's have that appear on the screen right now. There we go. There's our sums here in this table. Now what I'm going to do is I'm going to use this blue highlighter to represent event A, the spinner showing a 3. And what you'll notice is spinner showing a 3 happens down this vertical column right here. All these entries involve having a sum of 3. That's event A. And this happens 6 times out of the 24 entries on the table. Event B is the event that we get a sum of the die in the spinner being 5. I'm going to represent by the color orange. And anywhere where you see the sum of 5, I'm going to highlight it on the table as well. You'll see that it happens in 4 locations. So what I'm going to do is I'm going to write down both of these probabilities here on my sheet here. The probability of A was 6 out of 24, and that's also equal to 1/4. The probability of B, the sum of the spinner and the die being 5, happened 4 out of 24 times. That's equal to 1/6. And the probability of A and B, that's the intersection, where both colors intersect. Both event A and B happen. We show a spinner of 3, sum of the die and spinner is 5. That happened one place on this diagram out of 24. Because the probability of A and B is not equal to 0, these are not mutually exclusive events. They might be independent though, and we'll check independence by checking this formula. We will see if the probability of A and B is equal to the probability of A times the probability of B. We'll figure this out by substitution. The probability of A and B was 1/24. I'm just going to substitute that into our equation. The probability of A was 1/4. The probability of B was 1/6. And you can clearly see if you multiply 1/4 times 1/6, you will get 1/24. This is true. This means that the events are independent. And in real life, what this also means is that your ability to get a sum of die and spinner being 5 has no impact on whether or not the spinner shows a 3. If the spinner's a 3, you can get a sum of 5. If the spinner's not a 3, you're just as likely to get a sum of 5. So these events are independent. What I'd like you to do is I'd like you to pause the video, try problems 2 and 3 out, and we'll come back and take a look at your answers in just a moment. Okay, so on problem 2, we're looking at event A, probability spinner shows a 2, and event B, the sum of the die in the spinner is 4. What you'll notice again for event A is that we've highlighted in blue the spinner showing a 2. This happens 6 out of 24 ways on this diagram. That's equal to 1/4. The sum of the die in the spinner being 4 happens along this diagonal. This happens 3 ways out of 24, which is equal to 1/8. The probability of A and B, again this means intersect, are the places where the spinner shows a 2 and the sum of the dice in spinner is 4. And this happens this one way right here out of 24 events. These events still are not mutually exclusive because this probability is not 0. So what we're going to do again is we're going to check this formula to determine if the events are independent. The probability of A times and B equaling the probability of A times the probability of B. If it's true, the events are independent. Here, the probability of A and B is 1/24. The probability of A was 1/4. The probability of B was 1/8. If you multiply 1/4 times 1/8, you don't get 1/24, you get 1/32. These events are not equal. They're not mutually exclusive. They're not independent. They are neither mutually exclusive nor independent. For problem 3, here's spinner 4, 6 times out of 24. Event B are these two events. Sum of die and spinner being 3, this happens twice out of 24. We'll reduce both of these fractions down, 1/4, 1/12. The probability of A and B is where these colors intersect. This doesn't happen anywhere. You can't have a spinner show a 4 and get a sum of die and spinner equaling 3. So the probability of these events is 0. Since this probability is 0, we say the events are mutually exclusive. We don't even check independence because events cannot be both mutually exclusive and independent. As we move down our notes, the next problem is problem 4. It's a question that deals with independent events. What I'd like you to do is, using formulas, determine if these events are independent. Pause the video, read the problem, solve it out. We'll take a look at your answer in just a moment. Here you can let A be the event, red light at Zimmer Road. B can be the event, red light downtown. So we're going to check the probability rule for independence. If this formula is true, the probability of A and B equals the probability of A times the probability of B, then these events are independent. The probability of A and B is the probability of having to stop at a red light at both intersections. We know that value is 0.06. The probability of A, red light at Zimmer Road, is 0.15. The probability of B, red light downtown, is 0.40. And if you actually multiply 0.15 times 0.40, this is a true statement. Yes, it's equal to 0.6. These events are independent events based on the formula. In problem 5a, consider that this probability that a randomly chosen student from this group was running to be the probability of A. And in part B, when the question asks what's the probability a randomly chosen student was a 10th grader, let's consider that to be the probability of B. What I'd like you to do is I'd like you to pause the video, find the probabilities for parts A, B, and C, and then use this information to answer part D, dealing with our grade and type of exercise independent events. Pause the video, we'll take a look at your answer in just a minute. I'm going to again highlight the probability of event A in blue on the diagram. Probability a randomly chosen student from this group was running, we're dealing with these athletes right here. And for event B, the probability that a randomly chosen student was a 10th grader, I'm going to highlight that again in orange, and I'm going to highlight the orange entries as being the 10th graders here. And you'll notice we do have some overlap. For part A, we need to know how many students were running altogether. So if you add these three numbers together, you do get 87. And you also need to know the sample size or the sample space here by adding all of these entries together in the table. The total in this table is 145. So the probability a randomly chosen student from this group was running is equal to 87 over 145. For part B, what we need to know is how many 10th graders there are. And if you add this column of entries together in the 10th grade column, you get 60. The probability a randomly chosen student was a 10th grader is going to be 60 out of 145. And then for part C, the probability that a randomly chosen student was both running and a 10th grader, we're looking for the intersection or the overlap, the probability of A and B, or the probability of A intersect B. And that's these 36 kids that are both runners and 10th graders, 36 over 145. So to determine if exercise and grade are independent events, what we need to see is if the probability of A and B is equal to the probability of A times the probability of B. Because the fractions are a little bit not as pleasant here, we are going to convert these values to decimals, and we want to make sure that the decimal answers on both sides are exactly equal. Close isn't good enough. They have to be exactly equal to each other. So if you calculate 36 over 145 on your calculator, you're going to get 0.2482 approximately. If you multiply 87 1/45 times 60 1/45, you get 0.2482. These numbers are exactly equal. If you crunch them on your calculators, all the decimals line up. They are exactly equal. Again, close isn't good enough. If this said 0.2481 versus 0.2482, they would not be independent. But if they're exactly, perfectly equal to each other, these are independent events. So we say yes. In example 6, in a deck of cards, if you randomly pick a card, replace it, and pick another, what's the probability both cards are red? Let's talk about the first card being red. Probably the first card is red is going to be 26 out of 52 because there's 26 red cards in a deck of cards. If you want to call this 1/2, that's fine. The probability the second card is red should be exactly the same value because we've replaced the first card that we drew back in the deck. Let's say it was a King of Hearts. That's great. It's going back in the deck, so the King of Hearts is back in play again. 26 out of 52 is the probability the second card is red, which is 1/2. We're looking for the probability that both cards are red. That means the first card is red and the second one is red. This is basically the probability of A and B. And these events would be independent because what happens with the first card has no impact on what happens on the second card. Doesn't matter with what you draw the first card, the second card can still be anything. So we are allowed to multiply these two probabilities together, the probability that the first is red times the probability that the second is red. And when you multiply these probabilities, you get 1/2 times 1/2, which is 1/4.